We're on section 5.4, example 1. This is the first one that we're doing this curve sketching. Basically, we're taking the ideas from the previous 3 sections and putting them all together, and we should be able to use those ideas to take a function like this and graph it. Okay, so there's a lot of steps that you see on the worksheet for 5.4 and also in the book. So we'll just go through them. It says first, consider the domain of the function. Noted any restrictions? Well, this is a polynomial function. It doesn't have any domain restrictions. We're not dividing by any zeros at all. We don't have any square roots, so domain is all real numbers. Find the y-intercept of the function. So let's just go through this list here. The y-intercept. We get that by finding f of 0. So f of 0 would be whatever we get when we plug in 0 for all this. It's just a constant at the end, minus 10. So the y-intercept is at the point 0, minus 10. Okay, then it says find any x-intercepts by solving f of x equals 0 if this is not too difficult. Okay, well, in this case, it is too difficult. This is a cubic polynomial. It's pretty difficult to factor cubics if they do factor at all. This one doesn't, so it makes it even harder. So if you want to find the zeros, there's ways to do this without having to actually do it algebraically. I just put this in my calculator, and that's what I found where the zeros were. There's programs online, there's websites online where you can actually do this. Just type like zeros of polynomial into Google, and basically you just enter the polynomial. It'll tell you what the zeros are. Okay, so those are the zeros here. We found those with the calculator. Step 3, it says if f is a rational function. This is not, well, this is rational, but it's not. It doesn't have anything in the denominator. So no vertical asymptotes. Investigate symmetry. We don't need to worry about that here. Then it says next find the first derivative and then locate any critical numbers. Okay, so we'll do that next. Critical numbers. I'm going to just continue over here, since this is going to take a lot of space here. So critical numbers, we get those by finding the first derivative. The first derivative, setting it equal to 0. So let's do that. F prime here will be negative 3x squared plus 6x plus 9. Okay, and then we want to set that equal to 0, but before we do, let's go ahead and factor out that 3. Let's go ahead and actually factor out a negative 3. So if I do that, I'm going to be left with x squared minus 2x and minus 3. So we'll set that equal to 0. This is, again, to find the critical numbers. So notice here I can just divide both sides by negative 3. That negative 3 will be gone. So I'll just factor this. We'll get x minus 3 and x plus 1. And that's 0, so we're going to get our 2 critical numbers, x equals 3, x equals negative 1. Okay, so we want to use these to figure out where the function's increasing and decreasing. I'm going to make a small table over here. Again, this takes a lot of room to do this, so we'll go from minus infinity up to minus 1. We'll go from minus 1 up to 3. We'll go from 3 to infinity. Okay, so we'll just do what we've been doing in the previous sections. Find our test values, sine of the first derivative, and then what is our conclusion? Okay, so test value here, let's pick x equals minus 2. Let's pick x equals 0 for this one, and let's pick x equals 4 for this one. And again, I think the easiest way to do this is to use the factored form of the derivative. So in fact, that minus 3 is not going to matter as far as finding these critical numbers, but it is going to matter as far as the sign of the derivative, so I'll go ahead and put it back in there. So let's pick 0 first and just see what happens. If I plug in 0 here, I get a negative number there, and then I get a positive number there. But then I've got that negative 3 out in front. So I've got a negative, and then a negative, and then a positive. 2 negatives and a positive multiplied together is a positive. So we'll have a positive on 0. If I plug in -2, let's see what happens. I'm going to have -2 minus 3, that's a negative number. -2 plus 1, that's a negative number. And then I've got a third negative. 3 negatives multiplied together, negative. 4, I'm going to have a positive here, and a negative there. 2 positives, 1 negative, that's negative. So our conclusion here is the function's decreasing, then it's increasing, then it's decreasing. So we've got our intervals where the function is increasing and decreasing. Next step, find any relative extrema. So we can do that by noticing that the function changed from decreasing to increasing, and then it changed back at the other critical number. That means we've got a min and a max. The fact that it changed from decreasing to increasing means we've got a minimum at x equals -1. And we've got a maximum at x equals 3. Okay, so to find what these values actually are, we need to figure out the output values so we can actually graph them. It's going to be -1. And then remember, this is f of -1. So f of -1 is the value that we get when we plug -1 into there. So let's see, if I plug -1 in here, -1 cubed is a -1 times the negative that's already there. We got a positive 1. Plus 3, that's going to be 4 minus 9. 4 minus 9 is -5. Minus 10, -15 is going to be our y value for that particular minimum. And then we've got a maximum at 3. So again, this is 3. And then to figure out the y value, we have to plug that 3 back into the original function. I'm going to have to use a calculator on this one. So we get -3, square that. We get, or cube that actually, third power, plus 3. And then 3 squared, that's 9, so 3 times 9. And then 9 times 3 again, another 27. And then minus 10. So we're going to get 17 for that. So 317 is our maximum value. Okay, what next? Then it says, second derivative, we want to find inflection points and concavity. So I'm going to squeeze that second derivative over here. So f double prime of x is -6 x plus 6. Now if I set that equal to 0, I can just factor out that -6, and that's going to get us x minus 1. Set that equal to 0. X minus 1 equals 0 means that x equals 1 is a possible inflection point. Okay? So we'll make another table. Let's see, squeeze that under here. Another table. But this one is going to be pretty small. All we have is one potential inflection point. So we're going to go from minus infinity up to to 1. And then we're going to go from 1 to infinity. So only 2 parts of the table for this one. But it works the same way. Only now we're interested in the sign of the second derivative. And now we, again, use that to determine our the conclusion, concavity in this case. So let's pick x equals 0 for our critical number here, and let's pick x equals 2. I'm sorry, for our test value, not critical number. Now if I take 0 and plug it into the second derivative here, I've got, well, that's going to be positive, right? Just plug 0 here, get a plus 6. So second derivative is positive. And then if I plug 2 in there, I get a minus 12 plus 6. That's a negative number. So our conclusion is that this function is concave up, and then it's concave down. So we've got we do have an inflection point, and it occurs at x equals 1. So inflection point at x equals 1. And then we can find the y value for that, 1, f of 1. Remember, we're plugging this back into the original function to figure out where exactly that inflection point occurs, what the y value is. So we'll get 1. Now if I plug 1 in here, I'm going to have minus 1 plus 3, that's 2, plus 9 is 11, minus 1, or minus 10 is 1. So we've got an inflection point at that point, at 1, 1. So we've answered the question of concavity now, inflection points. Now it says, now we're going to plot all this stuff. let's go ahead and do that. I've saved this room here to do that. So let's see, we've got important values at -1 and 1 and 3. So I'm going to make sure that those are going to show up on our graph. And actually we've got these zeros here as well we need to worry about. So let's see, we'll go -1, -2, -3. That's probably good enough to get the zeros, and then we should probably go up to 5. And of course you have your calculator, so you can use it to verify that you have the right answer on this, graphically speaking. So let's go ahead and plot these zeros. -2.4, that's going to be about right there. 0.9, a little bit less than 1, so maybe about right there. 4.5, about right here. So this is the place where the function is going to cross the x-axis. And remember, how do we do that? We started out with this cubic. Really, the way that you would do this is you'd set that original function equal to 0 and solve it. Again, that's difficult to do because it is cubic, so I just use the calculator to find those. Okay, so there's those. We've got a inflection point we know at 1, 1, so that's going to be like, in fact, actually, let me draw the other ones a little bit first, since I think they've got bigger y values. So -1 and then -15. I'm not going to be too specific about the y values because they're kind of wide ranging here. So I'll put that down there and I'll say that this value down here is our -15. And then we've got another one, we've got a maximum we set at 317, so over here 3, and let's just go up here. We'll say that this point up here, that's 17 up there. Again, I'm not going to be too specific about scale here on the y values, just because the numbers are kind of big. Okay, and then I've got an inflection point at 1, 1. So since that's 17, 1 is probably going to be kind of small. Right about there, we've got an inflection point. Okay, so now the next step, it says to connect the dots with a smooth curve, being careful not to connect the points where the function is not defined. Well, this function is defined everywhere, so we don't need to worry about that. All right, so now let's make sure that it's doing everything that it said it was doing in our table and everything that we figured out. It's decreasing from -infinity to -1, right? So right there, that matches. We've got that point right there. Just try to connect these. It's going to do something like that. That's a minimum value here, so it's going to turn around. We've got an inflection point right there. What does that mean? It means it's going to come up here. It's like it's concave up until we reach that point right there. My graph is not that great. Until we reach the point there, then that right there, concavity changes. So now it's going to be concave down. And on a graph, it's kind of hard to tell where concavity is actually changing, but mathematically, that's what we got. So we know that it's going to change to concave down there. And then it remains concave down forever. So just go down like that. And we started with a cubic function that was negative, so this pretty much matches exactly what we should expect to see on a graph of a negative cubic function. So all of the calculus told us exactly what we expected, or we should have expected for a cubic polynomial. Finally, it says to check your graph on your calculator. If the picture looks different from what you've drawn, well, maybe you've done something wrong, or maybe you entered it incorrectly in your calculator. So I would suggest go ahead and graph that function on your calculator. Make sure your window is big enough to see everything. That would mean to have at least a y minimum of -15 and a y maximum of 17. You probably want to at least graph from maybe -5 up to 5 or 6 or something like that, just so you can see it. But if you do graph this on your calculator, you should see something, hopefully, that looks pretty close to what we've just drawn here.